So if anyone tunes in after, it's definitely varying times throughout the world. So if you can tune in at this time, I see we have like a good amount of people, but we will be having a AMA the day after for any questions that don't get answered today. They will be hopefully answered tomorrow within the Twitter Spaces and on a different platform. But yeah, we'll just begin. I will go over here. Here. So hopefully you guys can see my screen. I'll put it in slideshow. Can you still see my screen?
Yeah, we can see both the slides and we can also see you. So we've got a choice to switch between either one.
Perfect. Okay. So today I want to discuss the Entangled Rollup, specifically on what it is, how it fits in within ZKM, and how it all aligns with what we are planning for the future. From this, we essentially will expand into areas relating to cross-chain communication via ZK proofs. But I'll talk to you a little bit about what this all means, how this all connects to each other, and hopefully everything will be a little bit clearer after this brief presentation. Brief as in, it'll probably take about 30 minutes, but I'll go into it. My name is Pavel. I worked in the Metis ecosystem for about 3 years. Came on as an ambassador coordinator, after that integrations lead, after that currently doing DevRel Lead for ZKM. Essentially, I have been responsible for different types of bridging articles, NFT bridges, essentially different types of like token bridges as well, that I wrote about within these different articles, just the mechanisms and the designs. And so very familiar with these types of contests or these types of systems. And hopefully I can explain these systems in a bit of a better way to you today. I also built a, so developer, it's more of like a influencer marketing platform called Chorus. Essentially, that's where I have my Solidity or dev experience. And hopefully I can also communicate that as well, but not focus on just the dev experience. So I ideally want this to be a big just overview of what we're doing. So it's simple, easy to understand, and you don't need to have technical expertise to know what I'm talking about. So first, what is ZKM? To answer the question of what is ZKM, we have to answer what settlement is. And settlement is the idea of finalizing a transaction where that transaction cannot be reverted. So we have the concept of block times in many different types of blockchains. So there's different block times for a transaction to be posted in a block. In Bitcoin, it's about 10 minutes. In Ethereum, it's about, I believe, 12.5 seconds for a transaction to propagate and be validated by proof of stake. But the idea is, how long does it take for a transaction before nobody else can change it? Just because it's included in a block doesn't mean that the transaction is finalized. There can be things like miners coming in and let's say doing like a 51% attack, and then potentially removing a set of transactions and adding their own. We aim to make this process of finalization essentially unified across all different ecosystems. Now, to take a look at finalization, what this means in a different context, we can take a look at Kraken's essentially cryptocurrency deposit processing times. As we can see, there's varying different levels of processing times in these different networks. So basically, in order for you to cash out from Kraken, you need to wait this amount of time before you can do so. So in Ethereum, for example, you have to wait 14 minutes if the transaction is included in the next block. In Ethereum proof of work, so there was recently a fork where Ethereum switched to proof of stake. Well, one aspect kept it a proof of work, and you need to wait 3 to 4 days before this transaction can resolve. The reason why is because Ethereum Classic was actually 51% attacked, and some of its transactions got reverted. And as a result, there's increased, I would say, wait time before we can guarantee that this transaction cannot revert. Why this is all important? If we're basing our systems and connecting them together, we have to make sure that we follow a set of standard ways that is customized to different chains on what the finality of these transactions are. So using Kraken's basically estimations, we can see how long finality would likely take for any transaction that occurs. So what we're trying to achieve with settlement is actually universal settlement, where I can take any transaction. It could be a swap. It can be a swap. It can be let's say, a governance vote. It could be any type of data or information. And as a result, I can take this and I can be guaranteed that this executed on this blockchain without it being reverted. So that's what we mean by universal settlement, is the ability to connect independent, incompatible blockchains with each other and having them all finalize based on these different types of parameters that are listed in the finalization sector. So that's what we want to achieve. That's the goal, is universal settlement. How we do this is through an entangled rollup. And what an entangled rollup is a way to trustlessly pass messages from one chain to another using zero-knowledge proofs. What this means is essentially this diagram. Now this looks a little bit hopefully familiar. You've seen the white paper that we published. I think there were some revisions, but in the end, we have a way to communicate to different layer ones via the layer twos, and then have a way to generate proofs for this type of communication. So, for example, if I want to send assets, let's say to a layer two, so I can do this within the rollup contract. So I send a message, and then the rollup contract would then execute that on its own layer two. So let's say this one was going towards across incompatible networks, and this will make sense with the next few. So essentially, what we're trying to do is we're communicating between different types of blockchains via the layer 2s. And this can result in any communication done via these layer 2s. So even if they're non-EVM solutions, so for example, we can connect Ethereum to Avalanche, they're both EVM, but we can also connect non-EVM solutions to each other. So any type of L2 that's built on top of other networks, we can essentially use as this compatibility layer between them. So this is the idea behind the entangled rollup, is that each individual segment is an entangled rollup, and how they're all connected together is through quantum entanglement. And I'll explain that in a little bit. But essentially, we have this mechanism where I'm able to communicate between the different types of blockchains through layer 2s, and as a result, I can pass any form of message across any layer 2 to a layer 1 as well. So now we go into quantum entanglement. Whoa, this is something where maybe not many people are familiar, but that's okay. This is, I would say, the easiest analogy to understand how we do this through this entanglement. So quantum entanglement, there's this chunk of text, but what we're concerned with is of one particle is directly and immediately correlated with the equivalent characteristic of the others, regardless of separation in space. What we can actually do is we can replace these, so for example, particle for message, characteristic for properties, and space and blockchains. So we are using a similar process that a quantum entanglement provides for the communication of these different types of, let's say, information between different blockchains. And ZKM is building the quantum network using entangled rollups to enable universal settlement. And coming back to this picture, we are essentially taking individual, let's say, resolving, finalizing transactions, achieving settlement on one blockchain, generating a proof that this transaction happened and it cannot be reverted, and then relaying that to a completely different blockchain, and then communicating that within this network of entangled rollups, the quantum network. Let's take a look at an example. So Alice wants to transfer 100 USDT from Bob from Ethereum to Avalanche. So Alice ideally wants the bridge that she uses to transfer assets to be trustless, to be extensible, and to be liquidity optimized. So essentially, I want to make sure that the guarantees that my 100 USDT would be transferred is high. And I want to make sure that my money can't go missing, and that I can eventually get that money back because there's some liquidity backing that 100 USDT that I sent. To define a bridge, some people might be familiar, some people not, but essentially it's the way that we can transfer assets from one ecosystem to the other. And there's varying different types of designs for this. So there's like There's liquidity bridges. There's general message passing. There's different mechanisms as well for communicating with different nodes. But they all do the same thing. They all basically communicate messages from one chain to the other chain. Externally verified bridges. So an externally verified bridge, we send tokens to a deposit contract on the source chain. We essentially receive the request. So in this model, you have a different blockchain. You send a token, or you send it to a layer 1, which then gets relayed to a different blockchain. So if I'm going and transferring assets from Ethereum to Avalanche, there would be another blockchain sitting in between those other two. And then this is how, for example, a lot of bridges today work. The destination chain then mints or unlocks a corresponding amount of tokens. So for example, Seller Network is an example of a bridge that operates like this, where it locks and unlocks assets on the corresponding chains. There was multi-chain. Multi-chain actually had their own token that was minted and burned. So for example, if you deposited to a contract, they would give you, if you deposited the USDT, they would give you any USDT. And then as a result, you'd be able to take that any USDT and then redeem it on that selected network, assuming that there is liquidity for it. So here's some examples of externally verified bridges. It's essentially, we can see third-party validation for these different types of bridges, where I'm able to, so I take these transactions, I give it to them, and then their network processes and then unlocks a corresponding amount of tokens, or mints a corresponding amount of tokens, depending on this type of mechanism. But they do use their own blockchain, their own consensus, their own finality to achieve this. This is the most common type of bridge, and it's relatively easy to implement, but it does rely on some security assumptions. We have to rely that the network itself is decentralized and secure. We also have to rely and take into account the liquidity of these bridges as well. So if I'm transferring 100 USDT, that's probably a small amount, and most bridges can handle that. But if I was transferring, let's say, hundreds of millions of dollars, I'm a VC or whatever it is, then most bridges likely wouldn't have the level of liquidity for this type of operation. Can we use a layer 2 in this case? We go into natively verified bridges. A layer 2 is essentially taking the same mechanics of it's essentially building on top of a layer 1. And what does that mean? It uses the layer 1 as a settlement layer. So it splits execution and it splits settlement. Now, well, what is all of the these words? How they all combine? Well, what we mean is layer 2 has exactly very close security assumptions and by security assumptions, we just mean that it essentially relies on the security of the layer 1 to make sure that all of the transactions of that layer 2 are correct. And there's different types of mechanisms to do this. There's optimistic rollups and there's ZK rollups. But the idea is that they support general messages, but they're built on top of that layer 1. They're their own independent blockchain, but they have their settlement. Their transactions are settled on that layer 1, which provides them that security guarantees of the layer 1. And we call this natively verified. So here are some examples of natively verified bridges. We can see that we have some different types, but two main types are optimistic and ZK. For a natively verified bridge, if you're familiar with Metis, or if you're familiar with Optimism or Arbitrum, ZK Sync, there's all of these other solutions. You would essentially send your tokens to a bridge contract on layer 1, Ethereum, and then you would get the tokens would be minted on corresponding layer 2. So we would see that you deposited some tokens on a smart contract on Ethereum. And then from there, you go to the network and the network mints a corresponding amount of those tokens. Now, this is not the same thing as a mint, as in the multi-chain mint. When I'm using the multi-chain mint, I actually get not the actual token. So remember how I said any USDT, which is the actual token. So this is how it looks like, any USDT. That does not have any liquidity backing the actual token. That liquidity has to be provided by someone that puts some amount into the liquidity pool on the network. In which case, you would then have to swap it for true USDT directly on the network, which adds like the USDT that you've gotten is not always the amount that you redeem on that network. But the idea is that they're minted and burned on the layer 2, and they're locked and unlocked on the layer 1. We are maintaining 1-to-1, let's say, liquidity ratio for the amount of assets that are on the layer 1 and amount of assets that are on the layer 2. We're essentially saying that this 100 USDT that you've deposited to the layer 2 via the layer 1 bridge contract is minted, but you can redeem this 100 USDT back to layer 1. So even though it's minted, you still have liquidity backing on the layer 1, which allows you to withdraw from the network. Now, there are some limitations to layer 2s. One is that typically they can only communicate with the base layer 1 and with the same security assumptions and the same security guarantees. They can also communicate with other layer 2s that are built on the base layer 1. So for example, we have Hop protocol, which essentially uses the transactions that are posted on Ethereum. Like every time that a rollup has a certain amount of transactions, that transaction batch gets posted on Ethereum. And as a result, we can see all of the transactions that have occurred. And if we see that there's a bridge transaction among all of those transactions, we can then be certain that because it's posted on layer 1, on layer 1, I can unlock that specific amount on that layer 2 without waiting the entire, let's say, 7-day period for an optimistic rollup. For a ZK rollup, I think it takes 15 minutes for that state transition there, but in that case, you can just withdraw to the network. But as long as the data is posted on chain and I can retrieve it, I can then, with the same security guarantees as the layer 1, transfer these assets. And why is this important? The same security guarantees? It's because if you don't have the same security guarantees as the base chain, likely you are reducing it. Likely it is, you cannot guarantee that that chain is not controlled by a multi-sig, which then would be able to have your assets be withdrawn from the network. And I think some vulnerabilities, some major vulnerabilities actually happened in the case of Poly Network, in the case of Ronin Network. So billions of dollars are lost in these types of cross-chain communication. So that's why it's very important to maintain high security assumptions. We don't want to add any holes that people can siphon liquidity out of. This concept for having a natively verified bridge is a multi-chain and not a cross-chain. So what do we mean by multi-chain? Multi-chain is essentially, I am building applications on this layer 2, which inherit the security of layer 1. But this application itself, I cannot have it talk to other applications on other networks. For example, if I build a swap on one layer 2, I can't use it. I can't use the liquidity that I have on this layer 2 in the other layer 2. There might be ways where you can design, like with maybe hop protocol or something like that, where you can maybe facilitate this type of swap through them. But on its own, the swaps that are created on, let's say, Metis or Optimism or Arbitrum cannot talk to each other. And if they do, there's likely some security assumptions potentially. I mean, if you're using Hop Protocol, if you're using Beamer is another bridge that essentially is able to verify the layer 1 transaction. But the idea here is that when I build applications, I'm locked into that layer 2 ecosystem, and I can't use my liquidity elsewhere. I also can't bridge Ethereum to Avalanche because it's only useful for the layer 2s within these networks. So can we get native security and cross-chain communication? Here we have locally verified bridges, and we're taking a look at IBC. So IBC is a protocol. It is a communication protocol. If people here are familiar with TCP/IP, if the nerds here are, but if you're not familiar, essentially it's essentially just a way that computers can communicate with each other. It's just a standard of communication. It's like how you access websites, for example. That uses TCP/IP. So within here, we have different types of light clients that sit in between the two chains. And typically you have to create these light clients yourself. And then because we're using a unified protocol, we have native L1 consensus to achieve a bridge between two different types of nodes. Cosmos is one of the main protocols that implements IBC. And in this case, we have the locally verified bridges where we can communicate with any chain with no additional trust assumptions. But there is a big caveat, is that it needs to be adopted by the layer 2, or it needs to be adopted by the node. There needs to be tons of integrations that needs to be done in order for this adoption to occur. And it's quite limited to a specific blockchain type. I believe, so Cosmos, for example, if I want to integrate with Cosmos, I'm limited to Tendermint style consensus, which is how Polygon, like proof of stake, essentially a lot of proof of stake networks have Tendermint style, which is 2 out of 3 participants in the network sign, and then as a result, this gets propagated. So Polygon is probably the biggest chain out there that uses Tendermint style consensus for their operations. One additional thing is that if we're going for IBC, and let's say I'm doing the transfer from Ethereum to Avalanche, this is the user experience. I go to ibc.fun. I want to transfer 100 USDT from Ethereum to Avalanche. And then as a result, there's no liquidity there. And this is my user experience. Someone else needs to provide that connection. Someone else needs to provide that liquidity. And I'm not even able to transfer $100, even though it's super, super secure and all of this. So this goes to show that even super secure solutions, if they don't have the liquidity, are not going to get adopted. Maybe until there's like a point where there's I would say like profitability for this, but again, there's probably more opportunity in depositing funds than locking it in a bridge contract. So we've taken a look at 3 types of bridges: externally verified, natively verified, and locally verified. Now we have ZK bridges. So zero knowledge proofs. ZKM is essentially building a zero knowledge proof for the case of verifiable computation. So succinctness over privacy. Why we say that, or why we want to define these 2 types of use cases, but also say that we're targeting on the succinctness or the verifiable computation rather than the privacy. The main reason is privacy comes at a, let's say, cost to the user. If I want a completely private transaction to happen, I need to run the proof on my local machine. We did release our proof generation system, and it does take, let's say, most of these proof generation systems, especially generalizable ZK proofs, they do take a while for the actual proofs to be generated. And you do need a bigger machine in order to generate these proofs securely and privately. Because you would need a larger investment in order to use these types of systems. We took a look at this and essentially what we're looking at is we can actually take that computation. If, let's say, we don't care so much about privacy, all blockchain data is public. There's some networks where it's not, but if we basically just take that public data and we have a network of machines that have a lot of RAM, hundreds of gigabytes of RAM. Normal people likely don't have hundreds of gigabytes of RAM machines just lying around. So in this case, there can be systems where you can create and offload the processing for the ZK proofs. You cannot do the same thing with fully private systems. Fully private systems, you need to run your own machine, you need to have your own device in order to actually use it. And just like how we all have MetaMask, but we're likely not running a full node in our network, we're actually using Infura, where that's MetaMask's RPC, or that's MetaMask's full node. And in this case, most people are making transactions through that Infura RPC rather than running it a local node on this. So we see more adoption happening from this. We see that it's just simpler and easier to offload that computation. And because most blockchains have public data, it just makes a lot more sense in our case for this trustless, bridgeless cross-chain bridging, essentially. So the ZK rollup, like ZK Sync or Tyco, or there's others out there, but they basically take a batch of transactions, generate a proof, and send that proof to layer 1. Now, we look at ZK Bridge. They're utilizing layer 0 for liquidity and message passing. So the reason why we scratch off that using layer 0 as a means to bridge. Now, most people are okay with taking that bit of risk, right? There's centralized systems, and likely if they're making a lot of volume, these systems are pretty secure. But again, you're putting trust into these types of systems to facilitate this type of communication. So even though you're using ZK under the hood, you're still dependent on these liquidity networks, and you're still dependent on their relayers, you're still dependent on other aspects within their chain. So layer 0 is very extensible. So it works with other blockchains pretty seamlessly. They've integrated a lot. And it's also liquidity optimized. People have deposited many millions of dollars into layer 0. And as a result, the user experience of using layer 0 is pretty good. I can transfer USDT from one chain to the other chain without any hassle and with very minimal fees. So they provide definitely a useful service. But again, that comes at a cost. There's also ZK Link. ZK Link uses ZK proof generation, but requires liquidity providers. And remember when I said, when we looked at ibc.fun, where if there is no liquidity in one ecosystem, then likelihood is that you cannot use that ecosystem. You need to essentially convince liquidity providers to put in X amount of tokens on, let's say, Avalanche. And then as a result, because you have X amount of tokens on Avalanche, and I don't think that they actually connect with different EVM ecosystems, only within the different layer 2s on Ethereum. So I think they wouldn't be able to facilitate this cross-chain transfer because they're building a layer 3 on top of the layer 2s as well. But so you still need liquidity for these different types of systems. You still need a way to deposit So essentially, you're just passing the buck to another layer. But this design is secure. It depends entirely on ZK proofs, and it's extensible. Right? Like I can integrate any other layer 2 because it's based on Ethereum. So the entangled rollup, we are connecting layer 2s, and actually layer 1s as well, via ZK proofs. We've seen this diagram before. And a side note is we can support another form of rollup. So there's optimistic ZK, but there's also hybrid. And how a hybrid rollup works is essentially I can choose either to use the optimistic withdrawal method or a ZK withdrawal method. I don't know how many people here have Coinbase or Kraken or any type of exchange account. I think Binance as well does that. But there's an option for the traditional slow withdrawal. I think it's called an EFT transfer, electronic funds transfer. That takes roughly 3 to 5 days to resolve. But you can also do an instant withdrawal, but you're paying a % fee for that instant withdrawal. So think of the optimistic way to withdraw. So that 7-day waiting period, but you don't pay those fees that you would have paid if you did do a fast withdrawal. So sometimes for some people, they don't care if they get their money in 7 days, but for other people, they might care a lot, actually. And having that choice improves the user experience, improves the usability. So this architecture, this structure through these ZK proofs can enable these types of systems to be created and maintained. So why is a hybrid rollup useful? It allows users to withdraw. You have the fast but more expensive withdrawal, which is ZK, and the slow and a cheaper withdrawal, which is optimistic. Now let's take a look at one use case for a ZK bridge specifically tailored for liquidity optimization. So we're essentially taking a layer 2 plus a bridging protocol, which equals a universal L2. We are taking native verification with shared liquidity, and any deposit into the layer 2 would result in usable liquidity for the entire ecosystem. So this is where the power comes in, is that if I deposited X amount of assets on Ethereum, on Avalanche, on Solana, on Near, on Algorand, that would all affect the total liquidity of the entire network. And that's what we mean by liquidity optimization, is that those assets exist somewhere as a connection to all the networks. So whether you integrate Bitcoin into it, whether you integrate any other type of layer 1, those assets sit on those layer 1s. You can withdraw them on those corresponding networks. And it doesn't necessarily matter if I have $100 in Algorand or $100 worth of Bitcoin in Bitcoin, if I have $100 worth of assets on any other L1, there's likely an exchange that can off-ramp any assets that I receive. So there's exchanges that support Algorand, there's exchanges that support Near, there's exchanges that support Avalanche, Phantom, et cetera, et cetera. So this is what we mean by total unified liquidity. You just might not get the assets when you're wanting to withdraw everything into a layer 1. You might not get that on that specific network, but you will get it on a network which is participating with this universal L2 design. So here's how this works. Essentially, we would deposit 100 USDT to the bridge contract on Ethereum. As a result, on the universal L2 on Ethereum, this could be also existing layer 2s. So think of it like this. Metis can integrate this, Optimism, Arbitrum. You do have to have access to the bridge contract and the mint function on that layer 2 in order to facilitate this transfer, which is a big ask. But you're still able to participate within this network and integrate this within existing solutions. And since existing solutions relatively work the same way, it can just be very, very easy to add this module to what layer 2s already provide. So you would then, upon receiving your assets on layer 1, you would then burn a corresponding amount of assets on that layer 2. You would send this to a recognizable burn address, public burn address. And then from there, you'd wait for finalization. Remember, we talked about finality early on. You'd wait for some amount of finalization, some amount of blocks, some amount of time, essentially something that guarantees that the transaction cannot be reverted. And typically with a layer 2, that's when the transaction batch gets posted on layer 1. So whether you're using ZK Sync, whether you're using Metis or Optimism or Arbitrum, eventually some of the transactions get posted to layer 1. From there, we also want that layer 1, Ethereum, for example, to resolve. So it should take, depending on when that data is posted on L1, finalization should occur within that, I think, like 15-minute period that Kraken specified, I believe. Yeah. So assuming that the transaction batch is posted relatively quickly from that L2. But that's just small details. Don't have to worry about that. Essentially, we just generate a proof of burn from the finalized state of the blockchain. And the finalized state is that I burned 100 USDT. As a result, I removed 100 USDT from circulation from the networks. I can then have this proof that I have this amount of USDT. I burned it somewhere. I don't know where. It's like Schrodinger's cat in the entangled rollup, quantum entanglement, is that it's in a state where it's burned, but not burned. But when you reveal the proof, so when you look in the box, you are guaranteed an outcome. So in this case, I take this proof and then I can post it on the Avalanche layer 2. And as a result, because I post this proof, the Avalanche layer 2 can then take a look and say, hey, redeemed before. Because I need to specify which destination chain this proof is generated for. So then the Avalanche layer 2 basically checks all of the parameters of this proof. And then if everything checks out, that the proof was generated correctly according to these parameters, and it is a valid proof that wasn't redeemed before, they would be able to mint a corresponding amount of USDT on a completely different blockchain network, on a completely different L2, utilizing the same security guarantees as this L1. As the Ethereum L1, I'm generating a proof off of the data. and then I'm minting a corresponding amount on these other separate network. And then finally, I would be able to withdraw from that layer 2 on Avalanche to the layer 1, which then I'd be able to cash out or do whatever. So we have a lot of pros. One is that this mechanic is trustless. It doesn't depend on any blockchain, any intermediary between the two networks. So there might be certain things that happen here. For example, there might be a relayer network added. But the idea is that even if the relayer network goes down, even if ZKM goes bankrupt, you would still be able to take this and generate a proof from the contract. Oh, sorry, not from the contract. You'd be able to generate a proof from the data and then manually be able to withdraw on a different network. So you would still be able to use these systems even if, let's say, the infrastructure is no longer, or like the company isn't there. You would still be able to use the code that's published, it's open sourced, to be able to facilitate these transfers. So it's completely trustless in that regard. It's also interoperable. It can work with EVM and non-EVM blockchains. I can essentially take this and within this system. So if I go way back, right here and in here, I can essentially use it across different incompatible VMs. I know Wormhole facilitates a bridge between EVM and SVM, so Ethereum to Solana. Wormhole is an externally verified bridge. So they have their own consensus, they have their own mechanisms for the actual bridging. But again, it's externally verified or depending on them to facilitate and resolve these transactions. Versus communicating via the layer 2s. And we can see why this becomes very, let's say, lucrative for potential investors, is that when you're transferring assets, a lot of these bridges have maybe like $500 million in liquidity, potentially less, likely less on specific networks. So you'd only be able to transfer a small amount that's relative to the investors. Let's say I'm an investor, I'm a fund, I have $100 million and I want to transfer it from Ethereum to Solana. So Wormhole, I think, has the liquidity to facilitate that transfer. But essentially there's going to be fees involved. There's going to be, but let's say, for fun, we're transferring $1 billion. Now Wormhole definitely doesn't have $1 billion yet. I don't know if they'll have it in the future. But Wormhole isn't able to facilitate a transaction of this size, even if there's liquidity on Ethereum itself. With this universal L2 structure, we can come in and we can transfer assets from one universal L2 to the other universal L2 without needing to have liquidity on Solana, for example. So I deposit my $1 billion of USDT in the Ethereum contract to this universal L2. I burn the $1 billion from this universal L2. And then as a result, I generate a proof that I burned it. And then I send this proof to this other universal L2 on Solana. And as a result, I have just minted $1 billion worth of native liquidity on this L2 on Solana. I don't need a counterparty for it. I don't need liquidity on Solana because I've already provided guarantees, cryptographic guarantees using ZK proofs that I have the assets on Ethereum, which I burned on this layer 2. Now, let's say I want to cash out, like maybe there's like a meme coin thing, or there's some NFT collection thing, and I want to, I'm a VC, I want to participate. I do the thing, I participate, and then let's say I want to cash out, I want to bridge assets back. I can then burn tokens on this layer 2 and then redeem it back to Ethereum, which has, the $1 billion worth of USDT in liquidity. But likely within this system, any deposits that go to any layer 2 would then be able to be used across the entire network. So likely if people saw that, oh, well, $1 billion just went into this layer 2, likely something is happening. And so people can take, again, with the same security guarantees of using a layer 2, they can then deposit into this network in order to, see the FOMO or whatever it is. As a result, the deposits that are put on Solana, if I'm the VC that put in the $1 billion, now likely there won't be $1 billion deposited into this L2, but there can be like a few millions, a few tens of millions. But essentially, the VC can essentially take a portion of the funds and then withdraw it to the base chain as well, based on the deposits that other users have provided. So instead of relying on external liquidity providers to facilitate these transfers, that I have to lock up my $50 million in order to get 4% APY, that you can still use the liquidity within this network to do whatever it is that you're doing. We're making it liquidity efficient to move assets from one chain to the other chain. And as a result, this system is highly liquidity optimized because I don't have to have a counterparty. I don't have to have another person to act as the liquidity for that other chain. So let's fast forward here. And then I'm almost done with this, but it's liquidity optimized. So they're providing liquidity by depositing to the network, and any bridge funds that enter the network can be used across all networks. This is where the powerful aspect of this comes in, is that I do not have to rely on external liquidity providers. The users themselves that are entering into these layer 2s already provided the liquidity. I don't have to ask them to provide the liquidity again, since I'm using the mint function on that L2, which mints native liquidity on that L2. And as a result, we have L2 scalability benefits. So users are depositing to an L2. Whenever you're going to an L2, your transaction fees are reduced and the transaction speeds are increased. So this itself also provides a good incentive for people to want to use L2s, even though it might be completely new, right? If, when you hear, oh, we're going to make an L2 on Solana, you might say, well, Solana can process X amount of transactions per second. They already have the infrastructure to support all this, and it's like sub-cent transactions as well. True. But at the same time, if you can make transactions even smaller and basically transaction speeds or finalization of the transactions, if you can include more transactions in Solana, then it potentially has more incentive for people to come in onto the network. It's just all positives. If you're coming in and you're increasing the speeds, if you're increasing if you're decreasing the costs, and you're having a unified liquidity system, then all of these check all the boxes likely for people wanting to come in and use a new chain. Is that if you can say that, oh, well, there's going to be a lot of liquidity on there and it's very easy and it has the same security guarantees as the base chain, then that's an easy sell. Finally, generalizable. I can then send any form of message across any blockchain and have it have the same security guarantees as that blockchain. I do not have to have another network to facilitate this type of transfer communication. So I don't have to use Cosmos. I don't have to use Polkadot. I don't have to depend on another blockchain in order to facilitate this transfer. All I do is use ZK proofs as a means to pass messages across these different networks. Now, there are one of them I did mention earlier on, is that in order to have this system work, in order to have this unified liquidity system, you do need to convince existing L2s to provide access to the mint function when you have a correct burn transaction. When you have a correct burn transaction, then you're able to mint a corresponding amount of that asset, because if you can prove that you burned that asset, as a result, you can redeem that asset on a different chain. But again, you need to have that L2 to come in and adopt this. But that's okay. I see that there are services out there, Rollup as a service. Anchor is providing that. Gelato is providing that. And what do all of these, what we call them app chains, what do those app chains need? What do the app chains provide? Well, they provide increased scalability, and then specifically a blockchain that's built for their specific use case. But the biggest limitation for creating these types of app chains is liquidity. You want to incentivize people to bridge to your app chain versus someone else's, and then you're all fighting for that same liquidity, that same pie. In this case, if these app chains adopt and are part of this liquidity network, it's easier for assets to get transferred across many different types of ecosystems. Thereby, they are benefiting likely the most. So new projects, new applications are benefiting the most by being part of these systems. The older layer twos maybe don't see as much of an incentive to be part of this network because they already have a lot of liquidity on their chains. And then to say that, oh, well, you can bridge it between different ecosystems, that might be a bit not within their long-term vision of having liquidity in a single space. But at the same time, this system provides much better way for getting liquidity, especially for newer projects coming into this space, which I think we're going to see a lot more of these new innovative projects. And as a result, there's going to be a lot of interest from other people. And we need infrastructure to support this type of growth. Finally, dry spots. So as I mentioned before, within the example of transferring $1 billion to the Solana L2, there likely won't be $1 billion of USDT on Solana that people have bridged. There might be, but it's no guarantee. What is guaranteed is that your funds, or the claim to the funds of USDT or whatever it is available on any network that's connected as a part of this quantum network. So your assets can be withdrawn to another blockchain. But the idea is that most exchanges have the ability to withdraw from these different types of layer ones. Every day it matters less and less about which chain that you use. There's plenty of integration for a lot of these L1s out there, and plenty of ways to off-ramp on these different L1s. So the dry spots point is that you might not get the assets when you're trying to cash out directly on the network that you have put in the money because someone else might have withdrawn it. But you get a claim or a guarantee that it is somewhere as a part of this network. And as a result, you might get your 100 USDT on Algorand when you try to cash out. But then you can take that 100 USDT and go into an exchange and essentially redeem that for its dollar value. So this bridge design for liquidity optimization is trustless, extensible, and liquidity optimized. So Alice is happy. All right. Well, I know I said that's a short presentation, but I think I did take an hour and 10 minutes. So apologies for that. I guess if there is any questions, or if there is anything that's, if we have time for questions, but again, there will be an AMA tomorrow. You can give this presentation a listen. And then if you have any type of questions, you can, you don't have to have them now, but I will be there to answer any questions about this design on Twitter Spaces tomorrow. But yeah, I guess, do we want to take questions right now, Ben? What do you think?
Well, we've had loads of questions, to be honest with you, so it's kind of up to you, like how much more time you want to put into this. But,
yeah, absolutely. So I guess we could take like 3 questions, since, you know, keeping in mind of everyone's time. Well, ideally, this would have lasted an hour total, but.
Mm-hmm. Well, a recent question that kind of is in line with what you were just saying. So if a transaction, say Solana kind of breaks again and stops, and a transaction has been through the proving process and it's in a proof with a bunch of different transactions, it's in the relaying process. What happens if Solana then stops and breaks? What happens to that proof? Do all transactions get rejected?
So because we are operating off of the data on L1, so even if the L2 transactions have been, let's say, sent to Solana, if Solana did not get it via their nodes, and I know Solana has had these like issues where they were down for a few days, but if the data isn't able to be retrieved from layer 1, then you cannot generate the proof. So the data needs to be present on L1, and you need a couple blocks, let's say, ahead of the actual transaction that has burned the assets. So in this case, if Solana goes down and you try to generate a ZK proof based on that data, it will likely, well, not likely, it won't be able to generate the proof because it doesn't have that data that should be present on L1. That's why it's very important to have the L1 component and that finalization, or in this case, universal settlement of the actual transaction. So it has to, let's say, be executed on L2, propagated to L1, and then finalized, which is typically, you know, as we saw in the Kraken example, that can take between, you know, a few minutes to even days. So
Is there
Yeah.
is there any chance of this happening after the proof has been generated? So when it's in the relaying process, I don't know how quick that process is, but is there any chance of, say, Solana goes down during that part of the process? So the proof's already been generated. What would happen in that case? What would happen to that proof?
So unless Solana goes through a rollback, so let's say it rolls back the state of the blockchain, then that would pose a problem. But we haven't seen a rollback occur for example, I don't think, other than I think Ethereum after the DAO hack. So they did do a rollback of the chain, but that kind of messy because they sort of split it, and yeah, there's unless there is a rollback for the chain, which in those cases, like that's why Solana can go down and everyone still has their money, is that they it's just no new transactions can be posted.
Mm-hmm.
So everyone's assets are still safe. So as long as the transaction has been executed on layer one, or finalized, sorry, on layer one, then it doesn't really matter if Solana is down afterwards because the transaction has been posted and finalized on Solana layer one. But let's say, there's a threshold for the amount of blocks that you need for Solana. For example, if you need 100 blocks in order to guarantee that the transaction has gone through and it's not going to be reverted. In that case, if let's say there's been 99 blocks, then you can't generate the proof until the Solana network generates the next block, and then you can generate that proof off of the data, because you do need to have those block hashes for that data. So you're essentially operating off of the blocks that are being created on that layer one. Hopefully that answers that question.
Yeah, that's super clear. Many of the other questions I think may be a bit too extensive to answer now because of time. Somebody did ask about any other potential use cases for entangled rollups that you haven't mentioned. So is there perhaps a better way to ask is, are there any other use cases that can be integrated with this? For example, privacy use cases, or I think we spoke recently about reputation-based use cases. Or is this too big of a question? Should we go into this tomorrow?
Yeah, that's actually, so this is a recurring, so every Tuesday at around the same time, I'll have different slides for the different use cases. There's one thing that I didn't mention was that there was an EIP, I think 7.4 something. Can't think of the number at the top of my head, but
too many.
It's
EIPs.
Basically, yeah, exactly. Too many numbers in there. It's so with this, you're able to essentially have private burns. So I'll talk about this a bit, I guess in a week, but just to give a teaser, since you have private burns, you can essentially send assets to, let's say, the burn address on Ethereum is 0x dead, or most people use 0x00000, so on and so forth, because nobody has the private keys to that address, and everyone recognizes that that is a burn address. You can generate let's say, using ZK, you can generate a verifiable burn address that looks like it's a regular address. So it looks like I'm sending it to a legitimate user it's just a brand new account essentially. So, but it looks like 0xabc123 blah 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 blah. Because I'm sending assets to that account, there is provable deniability that I am using these systems or I'm using this as a privacy function. So people see that and see that it's like a regular transfer to this account. As a result, this is actually a burn transaction. So I'm actually removing funds from the network, but it doesn't look like it. It doesn't look like it because it's not going to the traditional burn address. But because I'm generating a proof that this is a burn address on this network, and I do not own, nobody owns the private key to this. As a result, I can then take that, generate a proof off of that data, because it is technically burned if no one has access to it, and then be able to redeem it on a corresponding network. Now, in terms of the, it's not fully private, of course. It's just the plausible deniability that I've sent, that I've used this system for privacy. But technically, it is possible to have private. Well, when you redeem it, people will know that you redeemed it. That's what I mean. So when you could still use it for privacy, except the privacy gets sort of revealed when you redeem, which is fine. It's kind of like, you know, if Tornado Cash, for example, is like, as soon as I use Tornado Cash, it's sort of, you're now in, your wallet is marked, and then it's like, yeah, like you're against like the sanctions and whatnot. So that's the way that it works with that. In this case, since you have plausible deniability, but again, like you can see that you're withdrawing from the system, but it looks like you're sending it to someone, real on the network, for example, which might be good if you're, if you want to escrow this into something else and then maybe withdraw. Like I'm still thinking of potential use cases, maybe like semi-private. If there's a way to make it fully private, that'd be interesting. So there's definitely some research there that we can think of, but definitely open to the community to also think of ways that these things can be utilized. But I'll probably give that presentation again like a little bit after. But I will share the EIP which I'm referring to. It's a 7503. So let me just type that in the chat. So EIP 7503. Yeah. I think that's all I can say about that for now.
Mm-hmm.
But I'll definitely have like a little bit more of that prepared for next week, which I'll talk a little bit more about the privacy use case. Even though we're not focused on the privacy use case, we're focused on the succinctness. If you have a beefy enough machine, you can technically create solutions using the ZK proof generation system. So that's entirely possible. But what we're focused on, again, is like the ability to communicate between different blockchains using zero knowledge proofs. So that's, I would say, more of what we're trying to do. And these are just some ideas for getting people in the mindset of like, how do I use ZK proofs to communicate between other blockchains? And then why is this the best way? Why should I even spend time learning this? Because it's the most extensible, safest system. And right now ZK proof generation for generalized computation is pretty inefficient, but every day it's getting significantly faster to generate proofs. So we can see this being adopted as a legitimate use case and comparable to how externally verified bridges work. Because when you do a bridge transaction, you do have to like sign a transaction, sign another transaction, wait like a minute, and then you get your funds. In the ZK proof case, you actually have to burn assets for the universal L2, and then you have to generate the proof, which can take multiple hours. So that's where, I've gotten feedback saying, oh, well, why would I do it for a couple hours when there's another solution that provides it for a couple of minutes? Well, try transferring $1 billion to a blockchain and see how that goes. But that being said, it's probably the niche use cases, but I think this would be the more cost-effective one as well. Sorry, I'm just rambling at this point, but
no, it all makes good sense.
It's
I think a good question is, or a good point is, like, we're still extremely early in the development of this, so we can expect proof generation to speed up immensely over the years, as time goes on. So yeah, it all becomes a lot more sort of feasible as. So one of the questions was, in terms of speeding up proof generation, is that entirely dependent on having better hardware, or are there like circuit level type improvements that can be made?
Yeah, better hardware, like hardware acceleration, for example. So a lot of like what we're doing is very much CPU focused, but as soon as you plug in, let's say, GPU or like specific hardware, then proof generation becomes that much more faster. Hardware acceleration, essentially. But also software. Right? There's different. For example, we're using Plonky 2 which is, I think, like the safest, but also the more optimized proof generation. It's a way where I can essentially take proofs, segment them into, segment them into different segments, and then process the computation on these segments, and then re-aggregate them together. So I can parallelize the execution of the proofs using this system, and then just combine them at the very end. So there's these different interesting ways for how we're utilizing. This is very bleeding edge. So definitely, like what I tell people is that still new, still early, still like lots to uncover, and definitely like to explore certain use cases, and hopefully that triggers something in someone that then causes them to think about things differently and maybe create like a similar types of system that works.
So probably just last point. So is there like a goal benchmark? So is there a time that you're ultimately aiming for with proof generation? Like, do you want to get it down to a second or a millisecond or a couple of seconds? Is there some kind of feasible end goal to all of this?
I guess proof generation on mobile phones would be, and have it ideally not noticeable that you've generated a proof. So I think that's feasible. But again, how much time will that take? Who's going to do it? Still unclear. But at the same time, we have a lot of smart people in the industry, but we definitely need more. So if this interests you, if this is like something that you see, like there's still a lot to improve, right? From hours to minutes to seconds. these are all exponential improvements. So definitely need a lot of people working towards the same way in this.
Mm-hmm. Cool, cool. Shall we wrap it up there then? And it's about an hour and a half now, so probably a good time to wrap it up.
Absolutely. Yeah. We'll answer any questions in the AMA tomorrow. If you have any questions, please post them in the Discord, and I will pre-answer them so that, yeah. So even if you can't attend the AMA, your question will still be answered.
Cool. Yeah, sounds good. I'll see you guys tomorrow. Yeah, same time, but on Twitter Spaces this time. So, cool. See you tomorrow.
Awesome.
Yeah, thanks very much,
All right.
Pavel.
Bye, everyone.
Awesome presentation. I think everybody will agree. So, yeah, thanks very much.